and AI via cross-layer hardware software co-design. So now we'll talk about optics for AI acceleration. And also at the end, I'll talk about how to apply AI back to photon design automation. So yeah, everyone knows machine learning has a wide application, both in data center for large models, language, image, video processing, and also on edge, right? Those low power, high speed processing for autonomous driving, and also has a wide application in security, defense, medical, even like IC design nowadays apply a lot of machine learning to improve the design efficiency and quality. And the main power source for those AI machine learning are two things. The first is the efficient computing engine, which is the chip, and also the software, right? The algorithm executing on it. So machine learning typically just shows very good scaling, right? So I directly quote data from like OpenAI and NVIDIA. As you can see, just feed more data into a larger model, you can always get a better performance. And in terms of computing requirements, both for training and inference, doubles every 3.5 months. And these numbers for previous small scale CNNs, for more than large language models, this number gets even higher. Compared to Moore's law, right, the transistor density doubles only every 18 months. So their doubling rate have a 5 times difference. So you can see those two exponential curves just have larger and larger gap as time goes. So to merge the gap between the computing and the AI model, we need some specialized and especially domain-specific computing hardware to achieve breakthrough both in the computing speed and the energy efficiency. So recently, there's a trend to evolve from the electronics machine learning accelerator to integer photonics. Compared to the traditional digital electronics like the TPU, GPU, and some more than analog neuromorphic electronics like the flash memory, memory stores, PCM, and photonics really shows the advantage in energy efficiency in terms of TOPS per watt, and also compute density in terms of computations per square millimeter. And so the current optical electronic hybrid chip already can achieve around 10 TOPS per watt energy efficiency. If we go to the fully optical chip, which is not the case now, we can remove the bottleneck between the electrical optical conversion and the memory bottleneck, we can go up to 1 million TOPS per watt. You can see a 10 to the 5th times potential. And you may wonder what's the unique point for photonics? What makes this huge difference? So here I'm gonna give a very quick comparison between the electrical computing and the photonics for computing. One of the main advantage actually for photonic computing is the high speed. Okay, the computing speed, the latency. So if you imagine a matrix multiplication unit, for example, in electronics, you can have the crossbar array and also the systolic array, right? Usually just take you 100 nanoseconds to 1 microseconds. It takes you a few hundred clock cycles to finish all the computation for the partial product accumulation and multiplication. But for optics, if you have this optical chip, right, photonic chip, just shoot the light through the photonic chip within the light propagation delay. Usually it's 5 nanoseconds. You can already achieve the matrix multiplication with one shot. And the second feature for photonic computing is the massive parallelism. Unlike the electrical circuit, right, made up by metal wires can only propagate one voltage or current signal at a time, there's no parallelism. And but for photonics, you're using photons for computing, right? Based on the superposition of light signal. And also you have a multiple dimensions of optical signals. You can modulate the light, magnitude, phase, polarization, wavelengths. You can have parallel information propagating through the same waveguide. And doing the computation, you were using the same hardware. So it's very suitable for ultra parallel computing. And the third one is energy efficiency. Unlike the electrical circuit, you have the RC component generate a lot of heat. Photonic circuit don't have the RC issue. Basically, it consumes zero state power if you use a passive photonic device. So the entire circuit is a pretty cooled down. So you don't have the heating density issues as the modern electrical circuits. And based on those three main advantages, photonic AI or optical AI as a new field is actually booming both in academia and industry. So starting from the very first demonstration from MIT, right? They published the first major photonics paper in 2017, and until now, 2023, you can already see a lot of different optical neural network designs with their experimental chip demonstration. The training pushed the hurdle from efficiency, scalability, robustness, etc. And most importantly, they are well supported in industry. And you can see you already find 10 plus startup companies like Matter, Intelligence, and other companies developing their chips for optical interconnect, optical computing, optical quantum computing. And also the EDA vendors like the Synopsys, Cadence, Ansys, they can support the hardware device simulation and layout automation. And most importantly, the foundry. Okay, the foundry can provide the device PDK for standard design and also chip tape out packaging, so we can experimentally demonstrate the usage of those optical hardware. So if you don't know how to use optics for computing, here's a short introduction called the Optical AI Computing 101. So the basic principle is very simple. It's based on light signal modulation. You can modulate the phase, modulate the amplitude of the light, and also based on coherent light interference and also photo detection, convert from the optical domain to the electrical domain. So here I show some examples how to use photonic device to implement the computing primitives in neural network. So the first one is scalar multiply, right? A times X. So instead of doing some multiplier, we're doing the analog domain. So we use the light modulator. So the modulator basically just scale the input light intensity with a factor of A. So the output intensity is just proportional to A times X. So it's very fast. Instead of this scalar multiply, optical device can also do matrix multiplication. For example, this device is a 2x2 Mach-Zehnder interferometer. We call it MZI. You can see the input vector just the x1, x2, and passing through this couplers for channel splitting. You have a phase shifter for the rotation of the phase, and also the second coupler can create some interference. And the output vector y1, y2, basically just a unitary orthogonal rotation of the x1, x2. And, and this 2x2 unitary matrix is very important building blocks for matrix multiplication. Okay, so instead of using W matrix times the X vector directly using the systolic array, we use decomposition. Okay, the photonic tensor core decomposed with matrix W using the singular value decomposition. So you get three matrices U, sigma, V. And U and V will be unitary matrices or orthogonal matrices in the real domain. And it can be mathematically proven by using n square of those MDI devices cascaded together as this triangular array style. And of course, you have other styles. You can implement arbitrary and unitary matrices for U and V. And for the diagonal matrix sigma, you can just put a whole column of modulators, right? You can implement sigma. And shoot the light in, carrying the signal, passing through U sigma V, and directly detect the output Y for your matrix multiplication results. So it's very simple for one-shot computing at the speed of light. And also we not only have the ultra fast parallel linear operation in the analog domain, optics can also do nonlinear activation functions. For example, we can use some central bulb absorber and optical RF material and also electrical optical conversion. You can create some certain nonlinear activation functions. So with ultra fast linear operation and nonlinear activation, we can build a hardware called optical neural network. We call it ONN. So optical computing actually shows a very wide application in energy efficient real-time machine learning. We have the edge computing, mobile computing on the edge. And also we have the high throughput data center processing. And some people also use for smart communication, okay, how 5G, 6G, distributed computing based on fiber optics. And also we can use this for scientific computing, okay, to do some drug discovery, solving the combinatorial optimization problem. All those advantages are not coming for free. Okay, it's not there is no free lunch. So designing those emerging photonic AI hardware actually has a lot of new challenges. The first one is a large area cost. I can tell you the optical circuits is very large, especially because of the optical device is very bulky. So here's the size for one MZI, just a single device. You can see the size is 40 times 200 square micron. Okay, the unit is square micron. Compared to the 7 nanometer digital adder synthesized using cadence tools, the area is only 5 square micron. And you can see the order of magnitude difference in the area, right? So typically, photonic circuit doesn't have a lot very high compute density, so it cannot squeeze a lot of components onto the circuits. And the second one is the robustness issues, because ultimately photonic computing is analog hardware, and everyone knows analog circuits is very prone to sensitive to variation, noise, processing errors, right? Manufacturing errors. So we can see a large accuracy drop if you just deploy your train model onto photonic hardware. And the third one is the adaptability issues. For training those optical circuits for different applications is much harder than training a normal CNN using PyTorch backpropagation. You can directly train it, but training optical hardware is much harder. So it's very hard to directly adapt those circuits for different applications and counter some dynamic variations. And the fourth one is the design efficiency. So we're talking about the whole life cycle efficiency, not just the hardware efficiency, but also the engineering efforts and the time you spend when designing those circuits. Previously, just pure on based on human design, you need high domain knowledge from the experts, so the design efficiency kind of low. And the key to solve those issues basically is the hardware software co-design and plus the design automation. So our contribution in this field already can see already covers a whole stack for photonic computing, from the hardware development, right? How to construct the efficient computing engine using photonic circuits, and also how to boost the efficiency, robustness, scalability through the circuit model co-optimization. And we'll also talk about how to use the hardware, directly use our hardware to reliably and adaptively to support various machine learning applications. And our works basically are cross aspects that covers area efficiency, robustness, adaptability, and form this whole matrix. We not only have the design, we have the simulation result, and also we have the chip tape out. We tape out those designs for experimental demonstration. So today's talk, I'm going to talk about 3 aspects. We will mainly focus on the hardware construction to accelerate machine learning using AI device, customize AI circuits, and customize the photonic architecture. And then I'll talk about how to reliably use on-chip training to improve the adaptability. And lastly, we'll talk about how to apply AI back to photonic design to boost the design efficiency and finally close the loop of photonic AI interaction. So here is a normal neural network, and one of the layers for matrix multiplication. So previously, as I talked about, you can use quadratically many MZIs to construct this array, right? Use sigma v, but those circuits are very bulky. Okay, mainly because the device itself is very bulky. So a very natural concept is to reduce the device, right? It's called device scaling, but you will encounter some physical limits because those MZIs, those waveguides, have a limit minimum width. Okay, it's around 300 to 200 nanometer. You cannot further scale down. So you can easily bottleneck by the physical limits. So natural concept is like idea. Can we compress the circuit just like when we compress the neural network, right? Quantization, pruning. Can we further compress the circuit, reduce the area, but maintain similar functionality? If that's possible, then we can squeeze more photonic tensor cores onto the chip. Then we can equivalently achieve higher compute density given the same chip budget. So the intuition is like the modern neural networks, including optical neural networks, are always over-parameterized. You don't really need the general matrices to construct their weights. Okay, so instead of using MZI to build arbitrary matrices, we can break the basic components like the MZI into the lower level basic devices, like the coupler, phase shifter. We break it down, and we construct a very compact circuit from scratch instead of using this predefined mesh. So we use analog end devices to build a butterfly style mesh. You can see the circuit area is much smaller, and we limit the degree of freedom, only implement the subspace of all the matrices. So basically, we treat the redundant matrix expressivity for higher hardware efficiency. So next, I can tell you how to construct this compact butterfly photonic mesh. So basically, we inspired by the circulant matrix multiplication. So we don't have the general matrix. We look at the circulant matrix. So basically, circulant matrix is the matrix, all the columns you can see based on the indices or the colors, just a duplication with a circular shift of this first column, right? just shift W1 to the second element. And this special matrix vector multiplication can be efficiently implemented using Fourier transform. You convert the input vector in the first column on W into the first domain through FFT and do element-wise multiplication. So this is the Hardeman product. And then you convert the results back to the spatial domain through inverse FFT. You can get exactly the same result, but the higher computing efficiency. And this algorithm has a very nice implementation to the photonic hardware. So you can implement the FFT to the optical butterfly mesh. Okay, by cascading the devices into this butterfly mesh and program the phase shifters, angles, you can implement the optical version of FFT. And you can pre-compute the first domain weights, FW, and implement to the element-wise sigma matrices. And the inverse FFT can simply map to the reversed butterfly transform. So this U sigma V can give you an optical version of those sigma matrix multiplication. And most importantly, those phase shifters are active devices. They are programmable. You can easily change those rotation angles to implement other transformations beyond the Fourier transform. So intrinsically, this programmable circuits is multifunctional beyond circular matrix multiplication, even though it's inspired by circular matrix multiplication. So if you want the circuit to implement execute in a low power mode, you can fix the butterfly transform, right? F and F inverse to Fourier transform to Hardeman transform, and you only implement the dynamic diagonal matrix sigma, right? You only program the sigma matrices. You can implement very low power structure matrix multiplication. And if you want to have a higher power and higher expressivity, you can jointly tune the U sigma V, all the matrices together, right? Then you can realize and customize the unit transformations beyond the Fourier transform and Hardeman transform, and you can express them arbitrary matrices approximately with 64% of fidelity, and this already gives you a very large degree of freedom to implement different matrices in your network. So to experimentally demonstrate the usage, we tape out those circuits using the advanced microfoundry in Singapore. You can see we have a 4x4 photonic tensor core, and we have this microcontroller. Through DAC, you can program the circuits for tensor computation using multiple wavelengths, and we read out the signal back to electrical domain through ADC, and then the microcontroller can do some post-processing. Okay. Basically, a large neural network can be partitioned into several chunks and sequentially mapped to those tensor cores. And we demonstrate the usage on different machine learning tasks. As you can see, we show ResNet 20, CFR 10 onto our circuits. We only have 3-bit resolution, which means we only have 8 distinct voltage controls for those phase shifters, and also we fix the butterfly transform. We only tune the diagonal matrix sigma. We can already achieve over 85% accuracy with real measurement data, not simulation data. And also we do some very interesting biomedical application like the COVID detection based on the chest X-ray image on VGG8. And you can see with the same setting, you can achieve over 96.5% accuracy to separate the COVID cases from the other normal cases. In terms of efficiency, potentially the peak compute density of our design can be over 200 TOPS per square millimeter, and energy efficiency is about 9.5 TOPS per watt, compared to state-of-art A100 GPU, Google TPU V4, and also a memory store crossbar array for analog electronic computing. You can see those two numbers are much higher than the state-of-art. Also, compared to the first design from MIT, the MZ array, our butterfly circuit is 2 to 4 times smaller in area, and also 5 to 13 times faster in terms of a shorter optical delay, and also is more robust. And turns out we can further compress the optical neural network by looking at the circuit model co-optimization. So previously we have the smart circuit design. Now we can co-design model and circuits to further shrink the size. And we're looking at the circuit sparsity, right? Doing some structure pruning. And during that circuit training, you can see the 4x4 blocks sometimes it's not important in terms of the circuit submatrices. It's very close to 0, which means you can directly zero out the entire K by K block and correspond to the elimination of this circuit. And if you zoom in, look at the detailed devices, you can figure out some of the phase shifters are very close to 0 degree or 2 pi, which means you can just remove the phase shifters, right? And they perform the same rotation. So we can do some column phase shifter pruning. We call it fine-grained pruning. So with those bi-level pruning, coarse-grained block-level pruning, and fine-grained column-wise pruning, you can reduce the circuit size by 66%, and also can maintain the accuracy within 0.5% accuracy. And also because you have fewer devices to generate less noise, and the circuit robustness is much better than previous, right? Even though you inject large device, noise and error can still maintain a relatively high accuracy. So our specialized butterfly transform kind of create a new research branch for specialization in photonic AI. So previously, people only look at different device, different implementation for universal general matrix multiplication. And our butterfly transform look at the very efficient subspace linear, right, using specialized hardware. As you can see later on, there are a lot of follow-on work from both automation, machine learning, architecture, and photonics community. Look at how to use customized structure like the low rank decomposition or other transformations to implement a very efficient linear operation in the subspace. So designing the specialized hardware with a hardware software co-design, you can achieve breakthrough in the scalability and efficiency. So how to further shrink the size, right? Previously, we talked about phase shifter couplers, MDIs, and this is the actual device I draw to scale. It's very bulky. And later on, people look at some very compact device called micro ring. So those ring structure itself is a very compact multipliers. But even though it's bottlenecked by the one operation per device, right? You can implement one operation per device. So the compute density just bottlenecked by one op per device. So can we further shrink the size and increase the compute density? So the idea is to move from specialized circuits to look at a customized device. Instead of using the standard foundry PDKs, we look at some customized multi-operand device. Multi-operand, by its name, you can tell we can implement multiple computations inside of the one device. Then the compute density is beyond one op per device. So it turns out we can squeeze vector dot product with a matrix vector multiplication plus some built-in nonlinear activation functions all together instead of a single device. Okay, then you can achieve an optical neural network with extremely high compute density. So we have the multi-operand ring, multi-operand MZI, multi-operand MMI. This is the multi-mode interference device. Previously, they're just a single device, but now we partition their controllers into multiple independently controlled segments. And then you can map a vector dot product or even matrix multiplication onto the single device, and together with some built-in nonlinear activation functions, for example, the tangent H function, and also this sinusoidal nonlinear activation functions. And those devices can be treated as a very compact photonic neuron. Okay, and we tape out those devices for experimental demonstration, and we can actually use them for a very compact linear operation plus nonlinear activation functions for a neural network. So here I want to show one example, the multi-operand ring. Okay, we'll call this structure squeeze light. So we squeeze more computation using the multi-operand device. So by partitioning the controllers into K segments, actually each of the controllers can be modulated by independent signal. You can see you have a vector, and each of the elements can control one segment, and each segment can encode the weights W0. And each of the segments have the phase shifter, and all their contributions will be accumulated through this ring structure. So this is a very natural W times X plus W times X plus W times X is a weighted sum. So this weighted sum is a vector dot product. Okay, so the round trip phase shift around the loop is a vector dot product. And the entire transmission, the output optical power is the nonlinear function of this round trip phase shift. And if you don't know the curve of this function, here is the curve. Okay, we utilize the left half of the curve. So basically, you can treat that as the positive half of the tangent H function. And this single ring is a K by K dot vector dot product. If you cascade multiple rings that is resonate at different wavelengths in this array structure, you can actually expand that to a larger matrix. Okay, we also have the positive rail and negative rail. So basically, we have a positive multiplication, negative multiplication, and the photocurrent, positive one subtract the negative one. Then you can have a differential structure. You have a positive value and negative value. We also have the learnable balance vectors. We can further modulate the intensity of different wavelengths, and then you can assign different importance to the different MORs. Otherwise, different MMR are have a normalized output intensity. So now we have the linear scalability, right? We can squeeze a vector k into one device. Can we further squeeze a whole k by k block into the device? Then we have a quadratic scalability. So it turns out we do a block squeezing. We also look at the structure matrices. For example, this is a circular matrix, right? The circular matrix with the same weights, just rotation-wise on different column, different rows. And for example, if you implement the first row, right, you just put x0 to w0, xy to wy, x1 to w1, right? If you want to go to the second row, you don't need to implement the second ring with the same ring, you just rotate the input. You assign x1 to w3, x1 to w0, x0 to w3, you rotate the input. So just rotate the input, apply to the same segments, you can implement the entire matrix. So you can reuse the same hardware, same device to squeeze the whole matrix. To further increase the scalability, instead of using more and more controllers, it will have implementation difficulties. We can look at the fine-grained sparsity. So, for example, we have an 8 by 8 block, 16 by 16 block. We can do some fine-grained sparsity to prune the circuit, prune the matrices. Only have 4 non-zero elements, and based on fine-grained circular matrix, all other rows will be pruned with the same pattern, and you can efficiently squeeze those elements into a 4 output ring. So it's very implementation efficient, and now you have a 64 times more scalability, only with 50% sparsity. And in terms, besides the hardware scalability, we have the ultra dense computing. Can squeeze the matrix into a device. We also look at the training scalability, right? You can already imagine it's very hard to train those devices. You need to partition the matrix into blocks and manipulate the behavior. You can see the GPU memory will explode even if you train a 2-layer CNN using those devices. So trainability basically matters a lot. And we look at the structure, we find a very nice correspondence between the depth-wise separable convolution to the photonic circuits. For example, you have the depth-wise convolution, basically is the channel-wise multiplication, and you can map those kernels to the multi-operand ring. And then the second stage is a point-wise convolution. Basically, along the channel with different wavelengths, you just have another weighted sum. So this point-wise convolution can be mapped to this point-wise convolution kernels. And then you can implement the fused separable convolution in a one shot. Should the light through the circuits, you can directly implement those 2 layers in a cascaded fused way. And then in the training, you can directly call the torch and calm instead of customized operation. You can see the runtime and the memory usage during training has order of magnitude improvement compared to the naive implementation. And besides the efficiency, scalability, we also look at the expressivity, right? So previously you have the structure sparsity, you can harm some accuracy. Now we look at how to compensate for this accuracy loss by using the learnable nonlinearity. So previously we talked about the nonlinear activation function for the ring. You can see the ring's nonlinear activation function can be tuned, can be learned. You can scale the curve. You can also shift the curve. Then the different neurons, different rings can actually prefer or learn different nonlinear activation curves. And this is very efficient to increase the expressivity and thus accuracy for this optical neural network. So compared to the previous design, the normal single operand ring wavebank, our multi-operand ring can be 20 to 30x more compact, use 8 times fewer wavelengths, the bandwidth matters, and also with the same area budget, we can be 5 times higher in compute density, 10 times higher in efficiency, and system-wise, we simulate this whole architecture, we can be 60% more efficient. And in terms of the accuracy, you can see it maintains a very high accuracy, recover the ideal simulation results. Okay, so previously we talked about ring, we talked about butterfly, but they're all based on the linear convolution or fully connected layers with the fixed weights, right? Because the weights are programmed by the electrical weights onto the device, onto the circuit state. And the problem is like every time you want to reprogram the weights, you have to reprogram do the SVD decomposition or change the state of the circuit. It's kind of slow. Okay, so we cannot do a real-time reprogramming. And also every time you reprogram this device, you have a high cost in terms of energy, in terms of the power. And also, sometimes for the ring, you can only implement a non-negative operations. For example, the input vector, assume is non-negative. So if you have a positive negative, you have a full range X and full range W, you have to use multiple computations, like the positive minus negative, right? It doubles your computation cost. So how to support a dynamic full range general matrix multiplication for a more advanced like the tensor computation, widely used in self-attention for transformer workloads. So that's the versatility we want to have. And turns out we want to move from the specialized circuit design to customize the architecture. Okay, so here I'm going to introduce the very first customized multi-core photonic transformer activator can both support a static which matrix multiplication for linear and also the dynamic tensor product for self-attention. And we have this nice circuits and all the signals are encoded in the optical dynamic signal. So we have the optical weights X and optical weights Y, and this circuit can directly perform ultra-parallel optical matrix multiplication. Then we can be very efficient for both with static computation and also dynamic tensor product. And also we have various architectural optimization to remove the electrical optical conversion bottleneck, right? So we, basically, which is the energy bottleneck. We have the optical computing core, which is the red core here for tensor product. We also have the optical interconnect, those waveguide for signal broadcast, signal sharing. We can directly reduce the signal modulation cost and the data movement cost. And we fully utilize the analog computing property. We do more computation in the spatial domain, in the temporal domain for partial product accumulation, so can significantly reduce the frequency for AD conversion. Then the ADC is no longer the bottleneck for the entire system. So we resolve the data movement through interconnect and resolve the AD conversion through temporal integration and analog accumulation. So compare with the normal design using microring or MZI, both on BERT, on the vision transformer workloads, we can be 3 to 6.7 times more efficient and 9 to 600 times faster in terms of delay. And we are more efficient both on tangent and linear operations. We also compare with GPU, TPU, FPGA, and our architecture we call DOTA is generally over 20 times more efficient in terms of energy and 100 to 1,000 times more efficient in terms of lower energy delay product, which really shows the promising application of those photonic actuator for advanced machine learning applications if you co-design circuit, the device, and the architecture. So for now, we talk about all the inference accelerator, right? For transformer, for CNN using photonic devices. And now let's deploy it on the real world application. But before you actually see a good results, you will see a malfunction. Okay, you will see a huge accuracy drop because remember, you have noise, you have variation. So the circuit itself is not reliable. And also it's very hard to adapt for different applications. You have a fixed functionality, it's not very interesting, right? So how to have a self-learnable photonic AI engine that can ultimately train itself to simultaneously solve the adaptability issues and reliability issues? That's our target for on-chip training. So training photonic neural network on chip is a trend. Okay, so instead of just training the model on GPU and with some noise modeling, deploy that onto photonic circuits at the traditional flow, and you can easily see a huge accuracy drop, even though you have a noise modeling, because the noise modeling is completely different from your actual chip, right? And also imagine you have the edge circuits, edge device, it's a drone, it's a robot carrying this photonic actuator, moving from one place to another. The environment will change, especially the temperature, right? The photonic circuit is very sensitive to the environment change. Then you have to query the cloud for GPU retraining and fine tuning. You have a high latency communication cost, and also you have the data privacy issues. For the better solution, you call it on-chip training or in-situ training. So you train and deploy this hardware or the model onto the same hardware. You train on the circuit and deploy on the same circuit. Then you can merge the reduce the gap between simulation and the actual inference, and this ultra fast training because you also leverage the ultra fast photonic computing for training, and then you can enable a local online learning on the edge. Then you don't have the communication cost back and forth between cloud and edge, and also you don't have the data privacy issues. So you have a lot of benefits using the on-chip training. On-chip training is the trend, but it's very hard. You can imagine the circuit itself is a black box. Okay, it's not like the tensor. You can know the input, output, and you can know the gradient using backpropagation. You know nothing. It's a black box. Okay, you only know the input and output. Okay, all the intermediate point instead of U and V are black box. You cannot use backpropagation or adjoint variable method used in inverse design to analytically calculate the gradients. So it's very hard to do optimization. And also the circuit itself is very noisy. So every time you forward a circuit, you get different results. But the randomness can easily cause diverge. And also, you're doing on-chip training, which requires the algorithm to be very efficient, very lightweight. You cannot have a very complicated algorithm. Otherwise, it's not even implementable on this photonic AI edge accelerator. So with all those constraints, previously people use gradient-free optimization based on genetic algorithms. You can see it's not very scalable. You can only train 100 different devices. And we propose a series of new on-chip training algorithms, include flops for zeroth order gradient descent, mixed train, we look at the sparse gradient descent, and recently we look at light published in NeurIPS. We look at the subspace optimization framework. We can finally enable a million parameter optical neural network directly trained on chip without extra circuit overhead. And the solution is co-design. We always customize the algorithms for the specific hardware, and we can have this 10 to 10,000 times trainability and scalability breakthrough by using the smart algorithms. So very first one, flops, is based on zeroth order gradient descent. So instead of doing costly backpropagation, we directly use the sampling-based and numerical differentiation. We forward the signal through the circuit multiple times, but every time we create a small perturbation on the phase shifter values, or rotation angles, then we can efficiently estimate the gradient. This is called the zeroth order gradient. Compared to the genetic algorithm where just device by device tuning, you can see our algorithm converging much faster, right? You can directly train 1,000 parameters. You can already see a 10 times scalability improvement. And also, it's 4 times more query efficient and can even counter some crosstalk and the noise issues on the circuit. And later we enhance the solution using mixed train. So the natural idea is like why we want to train every device, every circuit during every iteration. It's not very efficient and also it's not necessary. We look at the sparsity during training. Okay, we only allow a part of the device to be actively tunable. For example, the blue part are frozen, it's passive. We only tune those active regions. Okay, we select some important devices. And even though within those important devices, we don't need to train all of them each iteration. Okay, so every iteration, we just selectively train a subset of those devices inside of active region. We call it algorithm sparsity. So we have 2-level sparsity. We have a part of the circuit to be trainable, and we train a subset of those active regions during each iteration, and we can have a very high efficiency. And also we have a very high power efficiency because every time we do the parameter update, we prefer a low power parameter. For example, higher phase shifter rotation angles correspond to higher power, lower rotation angles like the 1 degree, 2 degree correspond to lower power. So we can naturally prefer small phase shifters during training. So overall, we can extend to 2,500 parameters with over 96% power reduction during training compared to previous solutions. And ultimately, those zeroth order optimization are not scalable to million parameters due to the curse of dimensionality. So the really scalable learning is enabled by subspace optimization. Okay, so previously we have the subspace concept for circuit design. Now we have the subspace in terms of the training optimization. So we claimed in-situ backpropagation is possible if you're using the subspace optimization. Okay, if you perform backpropagation in the subspace. So we freeze U and V because U and V it's not possible to calculate the gradient for U and V. We only optimize sigma. Okay, so we shoot the light from left to right, carrying the input vector through the circuits, and we pass it through V. And then at the end, you can actually get the intermediate result up to those red points. And if you get the upstreaming gradient, partial L or partial Y, you can reversely propagate the light reversely through the circuits, and you can get the gradients up to those blue points. And then you do a element-wise multiplication of those results, Y1 times partial L or partial Y sigma, you can analytically derive the first order gradient to those sigma matrices without the help of external computers. And turns out this first order subspace gradient is very helpful. You can directly use them to train million parameter optical neural networks without any scalability or training performance degradation. And this algorithm is enabled by the reciprocity, by leveraging the reciprocity of this optical linear system. So only need two forward and backward, you can directly calculate the circuit gradients. And we also further boost the efficiency because backpropagation is kind of costly, especially for edge devices. So we also look at the multi-level sparsity. So during the weight gradient propagation, right, we want to backpropagate the gradients to the previous layer. We can do some sparsity on the feedback matrix W transpose. Okay, so we intentionally select the important blocks on the each rows to skip some matrix blocks. For example, those white blocks are skipped. You can improve the efficiency. And also during the weight gradient computation, right? X times partial L or partial Y, X is a feature map. After input call conversion, you can skip some column vectors after the unfolding, right? You can further improve the efficiency. In terms of data, you can also skip some unimportant data, right? We only train on 50% of the data arbitrarily on each iteration, on each epochs. So with those three-level sparsity, you can have a approximation on the gradients. So we treat the expensive exact gradient for higher learning speed and efficiency. So overall, compared to previous method, on different benchmarks, up to 11 million parameters benchmark, even with the circuit error, our blue bar, the light solution, can efficiently recover the accuracy even with a large error and not large noise, recover the accuracy compared to the ideal pre-trained model. All other previous method based on genetic algorithm or zero-sort order algorithm will diverge or fail to recover. Okay, in terms of efficiency, because we have this three-level sparsity, we can be 30 times more efficient, even compared to the state-of-art machine learning algorithms for efficient training. And we apply this with algorithm for on-chip in-situ task adaptation. So we train on a tiny ImageNet, and then we adapt to CIFAR10 with our algorithms. We only train the sigma matrix in the subspace, and turns out it's enough. We can efficiently adapt the model to a new task, and it's 3.6 times faster than training from scratch. So that shows we can in-situ recover the accuracy due to noise robustness issues, and also we can perform task adaptation for transfer learning. Okay, so for now we talk about photonics for AI acceleration, inference, and training. And now we want to introduce how to apply AI machine learning and data automation back to photonic design to close the virtual cycle of photonic AI to improve design efficiency. Previously, we based on traditional manual design. You have some design experts to place those devices, construct the circuits, right, based on standard PDK devices from the foundry. And later on, it's better to move to an AI-enabled advanced design flow. Right, we have the automated IC design flow without human intervention, and also based on customized photonic structure with ultra-compact multi-operand devices. So the motivation here for AI is like, if you want to have some customized photonic structure, there's no way you can derive some analytical solution to describe the device behavior. You have to ask for the commercial simulation tools to perform a very slow numerical simulation, basically solve Maxwell equation to get the optical field and behavior, and then perform an optimization loop. And you don't have the gradient, you just keep querying the simulation tool. It's very slow. And AI can help you accelerate this process. So there's some prior work using convolutional neural network or something you heard about, physics-informed neural network, trying to minimize the error on the Maxwell equation to learn how to solve Maxwell equation. But those prior works are ad hoc to the specific structure, for example, this length, right? And also you need the PDE implementation. You need to actually implement those Maxwell equation. Okay, it's no easier than implement the simulator from scratch. All those boundary condition, initial condition, is very costly. So our idea is like, can we train a machine learning model can directly learn how to solve a Maxwell equation generally, okay? And this model can generalize the whole family of all the Maxwell equation PDEs instead of just a single simulation instance. And also we don't want to implement PDE. We want to save the Maxwell equation implementation efforts. It's pure data driven. You run a simulation, learn it, I can apply to different devices, different material, different input intensities, different light sources, right? Have a very high generalization. And our proposed solution published in Europe 22 is called Neural Light. Okay, so basically we construct an entire framework. We can encode the raw Maxwell equation observations. So the observation basically is the device description, for example, the refractive index for the material, the optical frequency for the input mode, and the optical light source, the magnitude, the phase, and also the unified solving domain, right? So within which domain you want to solve Maxwell equation. And then we have a very nice Maxwell encoder. Okay, then you can represent all those informations into a very compact tensor representation. And our model using a neural operator can learn the mapping from the Maxwell observation to the solution and directly give you a one-shot prediction in the Maxwell solution in the friction domain. Okay, and compared to the numerical finite difference friction domain FDFT simulation basically costs you 10 to 10 seconds. Our very fast neural network inference only takes less than 10 milliseconds. So we can easily have a 200, 400 times speed up compared to the numerical solver. So we have three major contributions. So first of all, we have a very nice PDE representation. So it's not like the nice image representation. You can directly throw that image to the neural network. Basically, you have tuple, you have matrix, you have scalar, you have vectors in the Maxwell equation. So there's no way your neural network can process those heterogeneous numerical format. So we have a wave prior. Basically, we encode the solving domain, the omega, the wavelengths, the permittivity, refractive index to a very nice generalized tensor representation. For example, you can see we have the light source, we have the material, we also have this wave prior, those synthetic wave patterns. Then we can encode the wavelengths. Okay, then we can throw that image into the neural network. And also we, inspired by the mask image modeling and computer vision, we also mask the image field. Okay, we mask the field, we only give the input port optical field as a hint to the neural network. And we want the neural network to predict what's the masked field on the right-hand side. Okay. Then we can encode a different light source. The second important thing besides data representation, feature engineering is the model design, okay? And previously we used the Fourier neural operator. So if you don't know what's Fourier neural operator, it's based on Fourier transform and matrix multiplication in the Fourier domain for kernel integral. Then you can progressively solve the PDE. So a Fourier neural operator is not very efficient, especially if you have 100 million parameters for those learning, then you can easily encounter overfitting. So we proposed a cross-shaped Fourier neural operator plus some convolutional feedforward network. As you can see, we partitioned the 2D FFT into column-wise and row-wise FFT. Then we can quadratically reduce the complexity in the frequency domain. And we also have the convolutional neural network at the end to capture the local feature. Okay, Fourier transform for global feature extraction, local depth-wise convolution for local feature extraction. But with global local feature, you can capture all the features and do a nonlinear transformation. So it turns out it's 10 to 100 times more efficient than FMO. And the training is also very important. You have the model, you have the data representation, optimization also matters. So previously we don't have enough data, so we look at the augmentation. Based on the linear property of Maxwell equation, we look at the superposition between optical signals. So with different stimuli, this optical linear system, the response also follows the linear combination of different response. Okay, based on the superposition, we can have a mix up, just like the mix up in the computer vision. We can use a superposition based on mix up for data augmentation to improve a much higher data efficiency. And also we can perform the one-shot multi-source prediction. We don't need to perform simulation on multiple sources and fuse them together. We can first fuse multiple sources and run a one-shot prediction, right? Ultra parallel. And also we force the light to learn interference, right? Superposition, but just means different light fields interfere with each other. So you can treat this as a very good visualization to help the model to be more generalizable. So with a better data representation, feature engineering, model design, and training, and you can use neural light for generalized Maxwell equation solving. And here are some examples. As you can see, we have a different device, and this is a multi-operand MMI and some edge device for optical mode conversion. And the first one is the predicted optic field, and second one is the ground truth field, and the third row is the error. You can see compare with the UNet, convolutional neural network, Fourier neural operator, some factorized Fourier neural operator. Our neural light is much better in terms of fidelity. We can achieve a 50% lower error, 40% fewer parameters, and then we only use 20% of the training data using our data augmentation. And here's a very nice animation. You can freely change the reflected index inside of the device. You can change the input wavelengths. Okay, and you can also change the device size in terms of the length and the height, and our model can give you 120 frame per second, basically real-time optical field simulation. For the engineers just using our tools, you can have a real-time response on the behavior. So you can enable very fast device engineering and optimization. So as a summary, we talk about the photonic AI acceleration, inference and training, and also apply AI to solve photonic hardware design automation problems for ultra-fast simulation. And ultimately, we can close the virtual cycle. Okay, and our contribution including different generation. We move from the standard optical neural network based on standard device, and then we move to the customized circuits, customized architecture for high efficiency and scalability. And recently, we also look at the AI-enabled automated optical neural network design to close the loop. Okay, and we have different photonic chip designs and validation to verify our designs for experimental demonstration. And all those co-design contributions are integrated in our open source library, Torch ONN. So basically, you can find a different optical neural network implementation and different co-design on-chip training, pruning, noise-aware training, quantization into our optical Torch ONN library to help you deploy your trained model onto the optical hardware. And if you're interested, feel free to check out and train your own optical neural network to play with those photonic devices. Okay, yeah, that's all. Thank you. I want to thank our collaborators, my PhD advisor, Professor David Pan and Professor Ray Chen from UT Austin, and other student collaborators for all the contribution in my presentation today. Yeah, I'm happy to take any questions. Yeah, thank you.
Thank you, Jiaqi. Thank you for a very nice and very comprehensive introduction on your amazing work. And so questions from our audience, so you can unmute yourself or input your questions in the chat box. Did someone raise the hand? Maybe you can directly.
Hi, Professor Gu. Thanks a lot for the very informative presentation. Because I'm from some electrical or digital IC field, so I'm not that familiar with optical hardware design. But based on my knowledge before, for general system, it's not only includes computing part, it also includes the storage and the communication part. So can you please also give some comments or some general concept based on these two aspects?
Yeah, sure. Yeah, probably I can show the architecture, right? We have the architecture, including all the components. For example, you have the memory, right? I have a memory hierarchy, DRAM, off-chip DRAM, on-chip SRAM hierarchy for global local buffer to hold the activation and memory, and also you have the interconnect, right? For the signal communication, for the data movement, and also you have the data flow, you have the computing part. So indeed, the memory is the bottleneck. If you go to some large language models, the computing is not a bottleneck. It's always bottleneck by memory. And also the data movement through the interconnect is also the bottleneck. Okay. And in terms of the computing, photonic computing only takes a small part. So some commercial accelerator from the Light Matter, the startup company, their data is like the optical part only takes 8% in total, right? ADC, DAC in total takes 20%, and the other digital electronics, especially data movement from memory, takes over 50%. As you can see, indeed, the still memory is a bottleneck. But we can use some smart design. For example, we can combine optical interconnect to at least remove the data movement cost from the electrical interconnect. Okay, so in terms of the memory load, we can use various compression from the algorithm-wise, right? Quantization pruning can reduce the memory bandwidth requirement. And also you can have a very nice SRAM band design. You can cascade, you can have a multiple parallel SRAM bands, and each of them have a time shift, right? And you use the time multiplex way to read data from those SRAM. And those SRAM can provide very high bandwidth to fit the high computing speed of those photonic tensor cores to remove the memory bottleneck. And also you can have a data, you can have a 3D stacking in terms of packaging wise, right? The SRAM, the electrical part, is directly on top of the photonic circuits in a 3D stacking, then the memory and control circuit is very close to the photonic circuit itself. We can further reduce the data movement cost. And also, the cost is actually in the AD conversion part, right? From analog to digital conversion, you can use the various optimization techniques to further shrink the AD conversion cost, right? By using temporal integration or other optical DAC, right? You can reduce the DAC ADC cost. So you can use some smart architecture algorithm co-optimization to reduce the bottleneck from memory and the data movement. Yeah. Hope that answers your question.
Thank you for your answers. Thank you a lot.
Okay.
I think there's another question in the chat box. Jiaqi, can you see that?
Okay, I can see it. In your neural network training, to replace FDTD, we're not replacing FDD, it's FDFD. What are the spatial and temporal step size of your neural network matrix size? So first of all, we're not doing FDTD, it's not time domain simulation, it's frequency domain FDFD. So we don't have the temporal step size. We're solving the steady state field. We only have the spatial matrix size. It's a very good question, right? So with different solving domains, different device size, the solving domain is different, right? But you cannot use a neural network for parallel batch inference, right? Because the different device have different size, different image size. So to unify the solving domain, we normalize the image to 80 by 384 image size. And of course, different pixels represent different delta X, delta Y, right? And as you can see, our wave prior can already encode this information. So this wave prior is A to the J, right? Encode the permittivity, the wavelengths, and also you can treat that as position encoding, delta LZ. Delta LZ is the pixel resolution after normalization. For example, each pixel can represent X direction 20 nanometer, Y direction 30 nanometer. Okay, so those resolution image can also encode in our wave prior. So we use this image normalization to ensure we have a unified image representation. Okay, I hope that answered this question.
Other questions from the audience? So actually, I have some follow-up questions for the previous questions about the memory. Yeah.
Yeah, sure.
You go back to the slides of your of the overall architecture.
Okay, that's our accelerated architecture.
Yeah. Yeah. So first, I was wondering, so how about like the energy breakdown for the your entire design? Like, how about the ADC and DAC, their portion for the energy?
Yeah, right. So different designs have a different breakdown. I didn't show the result here. So for this architecture, actually ADC power in terms of power is very high. The reason is like the frequency is too high. Okay, the frequency is too high, and also the resolution. Okay, because the resolution, if you use 8-bit, the ADC power is very high, and it takes almost definitely beyond 20%. And I don't remember the actual, yeah, we don't have the result here. I don't have the actual number, but the number is significant. That's why we want to use this temporal integration to reduce the ADC frequency.
Yeah. And also here, do you have any DRAM involved here?
Yeah, we have DRAM, we have ultra DRAM, yeah.
Okay, and how about like because we know that for the electro ASIC, so we have like the scissor array, so we know that how many multipliers and so in your design, how about a similar kind of the array size for your optical computing parts?
Right, so the array definitely is much smaller. For example, for this DPTC, we have multiple tiles, right? You have two tiles, probably we have two tiles. Each tile have like 4 cores, and each core is like 12 by 12 or 8 by 8. And it's a matrix multiplication. So basically, it's a 12 by 8 times 8 by 12. It's not a square matrix unit.
Okay, so in that case, I assume that you still need to perform kind of the time multiplexing style operations, right? And that means that
Yes.
every time you need to perform like the ADC DAC conversion.
Yeah. If you just do a very small matrix multiplication and then directly convert to digital domain, then you have a very frequent AD conversion. But this partial sum accumulation, you can do in a analog domain using some capacitor to do a temporal integration. Yeah. So this is very effective. If you accumulate 8 times or 16 times, then the ADC frequency reduced by 16 times, then the power reduced by 16 times, then it's no longer the bottleneck. Yeah.
But another problem is that because right now so all the computations in the optical domain, so you also need to every time, so another chunk of the data you want to compute, you need to another round of the laser, right?
Yes.
Because here you
yeah.
do not use the fully parallel, right? Because for this kind of the moderate workload, you must have kind of the still kind of partially parallel, right? So this is not just kind of another round of ADC, DAC, another round of kind of optical electrical conversion.
Yeah. We have nested loop. We partition them in the spatial unfolding and the temporal unfolding. So basically, you still need to scanning different chunks and map to this accelerator. Yeah.
So then how about like the breakdown for those the optical lasers, so the conversion between optical electronics? Yeah.
That's very good question. So in terms of laser, it's also a relatively large part because laser power is exponential to the resolution, actually. So if you have 8-bit, laser power is huge. And because our circuits already have a low loss, right? Low depth, you don't have a device cascaded. You only have one device directly go to the output at this point. So already have a low insertion loss. So it's also laser efficient, but laser power is still high. That's why we use a shared modulation unit. We have the broadcast. We only modulate the signal, for example, the X matrix once, and spread the input to multiple chunks. So kind of reduce the modulation cost. And also, you can have some optimization to reduce the laser power by optimizing the insertion loss for the device.
Okay.
But still, the laser power is a large proportion, I'll say. Yeah, like almost 40% if you use 8-bit. Yeah, so that's why our final demonstration is actually 4-bit. We have to train a low bit quantization to reduce the laser power. Otherwise, it will explode. Yeah.
Okay. And also, I'm curious about your next slide is about your comparison with the like GPU those stuff. So here this is kind of the energy reduction or the energy delay product that is for the entire end-to-end system or for one layer.
For entire system, we have an architecture simulation, which is simulate the bird where VIT, where DIT, and all the layers. And we have the memory stimulation from the cacti, and we have a data movement for interconnect, and also we have the computing core simulation, and we just add all the latency, all the energy from different components. Yeah.
Okay.
For all the layers. Yeah.
Okay, so that means that actually, so because your ADC and laser part that is occupies a very large portion, so that means that even in that case, you still have kind of more than 20 times reduction. So that means that your optical computing part is very, very energy efficient.
With those architectural optimization to reduce the bottleneck. If you remove all the architecture optimization, basically it still have some benefit, but you don't have this large number of benefits.
Okay, I see.
Yeah. So the memory part and ADC part definitely is very important. You need to.
Okay.
Yeah, the computing part is not the bottleneck. If you just have an ultra-fast computing core with very naive interconnect or memory hierarchy, then it won't work. Yeah, it won't work.
And then I was curious about then how about your comparison with other like the VIT transformer ASIC design?
Oh yeah, so
right.
For example, I think the heat VIT is the FPGA or the auto VIT. One of them, I think they're FPGA, right? Not ASIC. We didn't compare with ASIC, just FPGA. For those numbers, just directly use the number from their paper. And I'm pretty sure for FPGA, that's a real measurement result, not simulation result, right? And even GPU, we tested on A100 GPU on our machine. It's a real measurement result. But unfortunately, our data is not measurement results. It's based on simulation.
Okay.
Yeah.
Okay. And thank you very much. And another question is about kind of more general. So here you present that you work using like the MZI or using the oscillator ring or using like the multi-operand MZI. So we know that in the optical computing, so there are many different kind of the strategies or the solutions like the MZI of the ring or like detraction and so on. So I was wondering, so in your opinion, so what is kind of the future for the computing solutions in the optical domain? So which one kind of more promising, or which kind of more heterogeneous, or the hybrid solutions for that?
Yeah, definitely. So there's no winning device because different companies, different research group are focused on ring, MZI, or even in-memory computing, right? Phase change material, where based on microcode, right? Encoding the Ferguson domain. There's no winning solutions. The better solution is to go to hybrid one, right? For example, MZI probably is for static computation, and our design for dynamic computation. And the rings for ultra compact design, because the size for ring is much smaller. So if you have a very stringent chip area budget, you cannot use MZI. You have to use ring. So based on different constraints, you have to use different devices. And also ring is very sensitive to temperature. So probably if you have a fluctuation on temperature, you can use the corresponding best design, right? Based on some architecture design. And you can automatically select the hybrid settings. And the most importantly is like if you just look at the normal device, those devices are designed for communication. Okay, they're not invented for computing. And there are some other sub-wavelength devices for communication and computing. Sub-wavelengths just means all the structures are in a scale of 100 nanometer. So it's definitely much smaller, 10, 20x smaller than the wavelengths. Then you have very amazing behavior for those meta-surface devices. You can easily have a million by million pixels for ultra-parallel computing. And the people look at using meta surface, meta lines for ultra compact computing. Then we don't talk about A by A small matrix. Then we can easily talk about a million by million large Ferguson domain convolution. Yeah. And instead of just having integrated photonics on chip, we also have the free space optics, right? If you have heard about the diffractive optical network, the spatial light passing through some lens where the diffractive material have some interference and diffraction, and the light received by the camera, they can enable ultra parallel computing, right? But it's not very programmable. So you just combine the programmable integral photonics on chip and also the ultra parallel free space optics. I think the hybrid way will be the best for optical computing. But of course, you also combine with the electrical part. For nonlinear activation function, for memory, photonics doesn't have memory, right? So the entire system, I suspect, will be ultra heterogeneous, both analog, digital, electrical, photonics. Even for photonics, you have integrated for sensing for front-end processing, for the back-end, and the free space for front-end sensing and the pre-processing.
Thank you. Thank you very much.
Okay, yeah, thank you very much.
And any other questions from the audience? Okay, so if no more questions, let's thank our speaker again. So thank you, Professor Gu, to give us this very informative, very inspiring talk, and also thank everyone to attend our this week talk. And actually, this is our last talk in this semester, and thank you all for the supporting of our this seminar series, and see you next spring semester. Okay.
Yeah, see you. Yeah, thank you. Thank you.
Okay, thank you.
Yeah.
Bye.
Bye.